it is my pleasure to announce our 2DCC webinar speaker, Petra Reinke from University of Virginia. So Professor Reinke is going to be talking about 2D materials, structure, manipulation, and defects from graphene to silicene and TMDs.
It is a great pleasure to be here today and show you all the work we have done in the last few years. Actually, I think the oldest data set I'm showing today is nearly 8 years old, but it's still, I think, up to date. And we continue to work on these systems and materials. We have some samples which are also prominently featured, which came from the 2DCC and were grown at Penn State. So it's really a pleasure to finally kind of being able to show you what we use them for and, what has come out of all of this work. And while I did promise you some graphene or silicene to feature in this talk, I actually had to kind of slim it down because otherwise I'd be talking for a few hours. And this is kind of a portfolio of the work we have done. And in my talk today, I will focus really on transition metal dichalcogenides, tungsten diselenide mostly, and a little bit of molybdenum disulfide, which is kind of the grandmother of TMDs, the first one which was actually studied and presented in the literature as an interesting material to look at. So you can see here, it's quite a breadth of stuff we have done over the last few years. We modulated graphene by intercalation of fullerene between copper and the graphene layer. We synthesized silicene and silicene ribbons. And the next part, which is shown here in this portfolio, is what I'm going to talk about a lot in this presentation. And it's a question of tungsten diselenide and atomic scale defects and how they change when you start to anneal a sample. I will show an example where I worked with a colleague of mine, Professor Balachandran, with the question, how can you optimize or improve growth methods by combining literature search with machine learning? And I think despite the rapid growth of AI, there are a lot of lessons learned on that one, which I think is still really important for continuing this kind of work. The last example I'm going to talk about today, can we etch and write structures into 2D materials? And here the example material is tantalum disulfide as a metallic TMD. So let me continue here. And again, if you have any questions in between, please just feel free to interrupt me and do so rudely because I will not be able to check the chat while I'm talking here. So the main methods we've used in the material I'm going to show today is actually scanning, tunneling, microscopy, and spectroscopy. We also do a lot of work with X-ray photoelectron spectroscopy and ambient pressure XPS, but those electron spectroscopies figure much less prominently in my talk today, but we use that a lot for other work we do on oxidation of alloys and degradation and irradiation of TMT materials. So today it's mostly STM and STS. So STM is a method where you essentially use the tunneling current between a very sharp tip and the sample to do two things. One is you have kind of a geometric information because your tunneling current is very sensitive to very subtle variations of height or apparent height at the surface. But it is also gives you information about the local density of states at the surface. So both contributions are always present in scanning, tunneling, microscopy images, but we can also do spectroscopy, which gives us detailed information on the electronic structure at a very nanometric scale here within the images. And we use both of these capabilities of the STM in the work I'm going to show you today. So let me get started with the first question, which is about tungsten diselenide. It's the question, what happens with defects in tungsten diselenide? How can we introduce defects, which can serve as reaction sites for catalysis and functionalization? It can generate quantum states. Also, that is very tricky because you need a very specific type of defect to create the energy levels which are relevant for quantum states. Defects can serve as dopants for electronic as well as photonic devices, but they're also detrimental, like always, for electronic transport, electronic properties of materials. So they're both, apologies, good and bad at the same time. And the question is, which defects do you generate? Which defects can you control? Defect populations or the defect inventory? Can we tailor them? Which type of defects are even problematic? Which ones do you have on an S-grown material? And there's quite a lot of work which has been done on naked defects, which means defects which did not react with ambient water or oxygen. And there has been a work on dope defects, which are generated because of that reaction and interaction with some gas phase molecules. So we're not the first one and not the only ones who study these defects. They're challenging to study, but it's also very rewarding and very, very interesting field to explore here. What we really are looking at here is which defects are generated when we start to anneal the material. There are two reasons that's interesting. One thing is you might do a post-deposition annealing step. You might do that in vacuum, or you might do that in a selenium background pressure in this case. But we still don't know kind of which defects are generated primarily by this annealing. And the other target here is if you want to grow 2D heterostructures, you might deposit another material on top of your TMD, but you need to know kind of which defects are generated, which might live at the interface forever and can modify or even be very detrimental to the function of a device. So the particular material we're looking at here is actually a few layer tungsten diselenide grown on graphite. And this material was grown by Professor McDonald here at UVA, and it was grown by molecular beam epitaxy by MBE, which is a highly controlled way to study defects. The processing here, while the sample was transferred in air, but all the annealing steps were done in vacuum, so we expect that most of our defects are probably naked defects, which we observe. So let me give you a view of the surface. So this is how the surface looks like. You have graphite in that corner in the left-hand image. Can you actually see my cursor?
Maybe yes, not? Absolutely.
Okay, great. And you can see this here. This is the first layer tungsten diselenide, and you can see a very short wavelength Moiré structures, and that comes because your graphite and your TMD have very, very different lattice constants, but both are hexagonal. You can see second layer TMD here, which is an island here in a much larger area, second layer. And you see a little bit of oxidation here at the perimeter of the etch state. These are the defects we're actually not going to look at, but you can also confirm the height of your TMD and a first view at spectroscopy. And you all know that the band gap changes from 1-layer to 2-layer TMD. And you can see that here. This is where your band edge is. This is the other band edge in the valence band. And you can see how the band gap is a little bit reduced if you go to an additional layer of the TMD. So these are both checks, not just that we got the right material, but also to test our system in terms of spectroscopy and the imaging capabilities. So if you go to the right-hand side, that's an image how the material looks like after annealing for 30 minutes and 600 degrees Celsius. Yes, we went to a really high temperature very quickly. What is quite amazing is there are really still large areas on the sample, which have very, very few defects, but you also see a pretty high concentration of defects on these surfaces in the second as well in the first layer of the material. And you have some defects which are really large, and I show a sample here on the right-hand corner, and these are essentially holes in the material. Which is quite intriguing, and they still generally tend to retain a somewhat spherical shape, which is also, we found quite surprising in this context. If you look at the band gap, and this is a band gap which is determined by doing kind of spectroscopy over the whole image. So you essentially get a map. You have like 1,024 pixels, and every second pixel is a spectroscopy information. So you can average over the band gap distribution on the pristine material and the one after annealing. So you can see before annealing, the width here of that distribution comes from having first and second and third layer TMDs. But after annealing, you can see that you have a much broader distribution just of band gaps, and that comes to the emergence of defects and the distribution of defects on the surface. Let me go you to the next one, which starts to look much more specifically at two things. And these two things are not just the band gap, but the position of the valence band as well as conduction band edge, because that allows us to look at, do we make an N-type or a TP-type defect, or do we make an electronically neutral defect? Because we know the position of the Fermi level, and we can measure from our spectroscopy data sets the position locally of valence band and conduction band extrema. Let me point out these spectroscopy data sets, current voltage characteristics, were obtained at room temperature, which is actually quite unusual, but our system is better equipped to work with annealed samples and higher temperature experiments, and it therefore does not have a cooling capabilities. And for that reason, what we can determine reliably is things like extrema of the valence band edges, and consequently band gap distributions, but we rarely focus on the exact shape and peaks within the spectroscopy data, because we have a little bit too much noise and a little bit too much drift. Also, it is very small for a room temperature instrument to do so. And we also want to measure relatively fast to beat the drift, which means we numerically differentiate to get the local density of states instead of using a lock-in technique. Here in these two graphs, you can see that we determine for all the data sets we have in our images, we do the second derivative, and from the second derivative, we get the position of our band edges. So the broken line here is the second derivative, and the red one is average spectra taken over a specific area within our imaging window. And again, as mentioned from the IV curves, you can get, using the derivative and the division here by I over V, in order to get the local density of states at the position where you do your measurement. So you can see if you anneal your sample, instead of these very sharp distributions for valence band edges, you do get, as expected from already the band gap distribution, you get changes in the position of the valence band as well as position of the conduction band edges. And that is what we use in order to figure out for specific defects whether they are N or P doped. And if you go to the next one, what we did next is we looked at smaller areas, and these are just a few nanometer square images, and we started to classify our defects. So we have a whole zoo of different defects. So we classified them by two things. One is their geometry. How big is their imprint on the apparent height? How are they, in terms of shape, in terms of contrast within the images? And I'll have some comment on contrast in empty or filled state images in a moment. Are they P or N-type images? And then we classify them accordingly. So in the whole image set, taking out these really hard holes, which we could also detect, we have 5 different types of defects, and they're all relatively large defects. And we can call them compound type defects because they involve several atoms and the reconfiguration of the defect after the loss of, most of the times, we think that's loss of selenium, but we also have defects which come from essentially subsurface degradation of the material. And one of these is this NP-type defect, which is neutral electrically. So your Fermi level is essentially in the center of the gap, but you can still figure out very nicely the structure of the TMD in that image, but you know that your apparent height, and this one changes, so this is most likely a selenium cluster which is buried beneath your first layer here. So that means you don't just degrade the top from the top into the bulk, but you also start to degrade beneath the surface, essentially. So we have typical vacancies. These are generally selenium vacancies, which we can identify. And here you can see the distributions for the position of the valence and conduction band edges here in that system. And you can see that for a P-type defect, an N-type defect, and another N-type defect where your conduction band edge essentially moved, but your valence band edge kind of stayed in the same position. And let me clarify, we do here use as an energy comparison, we display this as a change of valence band or conduction band position compared to the tungsten diselenide, which is around that particular defect. So all these values are determined within one single image and within one single map, which takes out of the interpretation the question of local variability within the spectroscopy data sets. So these are the first 4 images I wanted to show you. And you can see also, which is something we do pretty often, is the question to beat kind of the statistics in this case. That continues to be a challenge in STM imaging as well as spectroscopy, because you image a relatively small area, but you would like to get a really comprehensive view of your defect distribution. And those goals kind of compete and sometimes also are not compatible because STM is time consuming, but STM also gives you the information you are after. And I comment on that also in the next few instances of examples I show you. So if you look at this one, the other thing you can do from spectroscopy, so this is the STM image. And this in B, you can see essentially a slice. So that slice means you look at the intensity in the image, but you look at it at a very specific voltage. And what you can see is this defect, which is called P1. The numbering is somewhat arbitrary. So we see this defect here very clearly in the integrated STM image, but we actually don't see it anymore in this specific empty state image slice, but we see the defect very nicely at this position here in terms of voltage in the filled state image. So the reason for that is the following, and here's a large image of that defect. If you look at the position of your valence band maximum, it is pretty stable. And the valence band maximum is very close to these image slices, so you always have contributions to your image. If you look at the conduction band minimum, my apologies, you can see that as you move closer and closer to the defect, that conduction band minimum moves to a larger and larger energy value. Which means, firstly, bizarrely, your band gap gets larger in this case as you approach the defect. That's why I chose it. It's really an unusual case. And you can see that, I twisted my mouse here. And you can see here very clearly that because your image slice is at 0.85, at some point here as you approach the defect, you actually don't have any more states to contribute to your tunneling. So that's why you have a contrast inversion in your image. You can do this for each one of the defects individually, and these images give you a very good idea about when does this defect contribute to the tunneling current and when does a defect stop contributing to the tunneling current. As to the question why the band gap increases for this one, this defect also shows in the STM image a deformation, so an increase in apparent height. And we actually think that this defect is because locally your layer has delaminated from the remaining other TMD layers. And for that reason, you kind of have a little bit like a bubble here. So instead of a two-layer TMD at that position, you just have a single-layer TMD and therefore a larger band gap. For the sake of full disclosure, we have not seen these P1 type defects very often. But that gets to the question, is it just, a very, very rare defect? Or is it just because we were not able to capture fully the statistics and distribution of the defects? And that's a very, very relevant question if you want to really study defects and how they influence your overall properties of the material. Ideally, our dream is to measure these defects within a device configuration, but very often due to transfer, you have residue on the surface and you're just not able to look at these defects anymore with STM, which I think is rather sad. Let me summarize here the defect inventory, which we set up. And specifically defects which are labeled here N3. I give you also a comparison with a DFT calculation. A single vacancy created by a loss of selenium, a double vacancy, and a triple vacancy. And you can see you have an increasing number of states coming up in the gap. And these are all states which would lead to N-type doping. The reason I am only showing to you these DFT calculations, because all the other defects are significantly larger in terms of their geometric imprint. Let me go back a few pages. You can see that here really well, while the N2 type defect is an N-type defect. It's also pretty large and it looks kind of gnarly a little bit. So these are compound defects where your system around the defect has relaxed significantly. So it's very hard to really model them with DFT because you don't really know which geometric structure to use for your modeling. Again, it's really nice that a lot of the TMD surface is still intact, but depending on what you want to do, these defects can or might ruin your day. Experimental challenge, local probe compared to the drive to get faithful summary of the defect inventory. There are some new methods which try to automate the measurement. So you can reposition your tip and sample much larger areas of the sample. These are very new developments and we would really love to implement this one. There's also a data challenge which comes from the DFT side. And the analysis of the images, the more images you get, the more difficult and more time-consuming a reliable analysis gets. We analyzed about 40 defects, which I think is about the limit in terms of doing this by hand. So we would need a library of defects, and there also is a drive in the community to get there. Let me point out, we're right now doing something which is more crazy. We're trying to use low energy ion irradiation to really be more targeted in the introduction and defect. And this work also benefits greatly from samples we're receiving from the 2DCC. So let me go to another example. And that's the question, what happens if your tip damages your TMD? This is not generally an issue with these very commonly used semiconducting TMTs, the tungsten and the molybdenum carcinogens. But it pops up in the literature on a semi-regular basis. For metallic TMDs, they're much more sensitive to the interaction with the tip. It's most likely chemical reactions which are initiated would lead to the desorption of tantalum disulfide molecules. They are tip-induced reactions. Let me point out that while this is annoying, if you want to study these materials, it's at the same time an opportunity. The question is, can we control how we structure the TMD surface to have a lateral structuring, a lateral template, which we can use to make not just stacked heterostructures, but can make really integrated heterostructures. We don't have an answer whether this is possible, but we do think that tip-induced writing could be a way to go there. So the first thing is, can we even deterministically write any structures here? And let me show a movie just to wake up everybody a little bit here. Let me show a movie of how that works. You image for a very long time, and you can see that you generate more and more of these vacancy islands on the surface up to the removal of complete layers within the area of the image we are doing. And again, these are samples we received from the 2DCC. We're very, very happy about those. They allowed us to do all of these experiments without having a large, synthesis set up here. So let me go to the first question, which I'm sure comes to your mind, which is this really a tip-induced writing? I can tell you, I forgot the image here. I'll show you later to confirm that. Let me show you first the sample we started with. So you need to know what you start with before you can do anything to it. So the STM image here on the left-hand side, it's a very large-scale image. You can see that imaging at a very large scale gave a lot of streaks, which often is an issue with STM. So this is a stitched image, which has a lot of segments, which are smaller images, which are now kind of stitched together to give a higher resolution and better quality images superimposed. And what we see relatively frequently on this sample are these grooves here, these line-type defects, which look a little bit like drainage patterns. We suspect this is a remnant of the growth method itself. We cannot tell whether this is typical just for this sample or whether this is just all of the CVT grown samples might have in parts of the samples these patterns. You can also see these buried line defects. These are line defects from the surface, but they are overgrown with the next few layers. The reason I show you that is because they're also of interest for the etching pattern which develop. We can get atomic resolution. We also had STEM imaging done at Oak Ridge National Lab with Dr. Hachtel and Professor Burns, who is also here at UVA now. We were not able to find these buried line defects, which kind of points to the fact that they are rare and not very common in the samples. Okay, let me go to etching, and let me show to you why we know it's tip-induced. So we imaged an area here. We got these tip-induced formation of vacancy islands. We have a scanner boundary because, well, after doing that for a while, and here you see a subsurface line defect, we zoomed out and imaged a larger area, and you can see that this larger area has much, much fewer defects than the one which we scanned for quite a long time. So I can show you that, confirm that the tip really does the writing of these structures. The next challenge, because we don't want to just write something and say, hey, it happened. We actually want to get the kinetics, the growth. How fast do they grow? And then, because we need that information in order to do a targeted writing at some point in the future. So the challenge, if you've ever tried to analyze an STM image, which is a little bit streaky, I can tell you this is really difficult with any of the classic tool like Fiji or ImageJ. It works very well if the analysis is done by a student. However, analyzing 400-500 images in a stack is just a punishing, time-consuming task. We found a relatively new AI tool. It's called Segment Anything, which works reasonably well. And I'm sure there are more and more tools which will come up, which are very useful and allow us to really do this type of analysis. So let me show you kind of which type of processes we get on the surface. And you can see here, this is vacancy island number 5. We can completely remove small islands. So if you go from this A to step B, the small islands are completely gone. We have a new set of islands, and these islands coalesce, which you can see very clearly if you analyze the perimeter length or area as a function of time. And you can see the break. Your perimeter is essentially conserved, while the area starts to increase at a different rate. Well-behaved island will just continue to grow until it hits another island, at which point you start to see the coalescence phenomena. You can see that happen a lot here. You have this, the island number 3, which looks somewhat like the head of a horse. And you have cases where the subsurface line defects actually pin the progression of the etching, and you can see these little corners here develop because the recession is delayed if you move along a line defect. We call that pinning, and it's also seen quite frequently. So if we now, you can see here the line defect again and how the recession worked here. And you can see these corners here, which are pinned at that line defect. So any inhomogeneities on the surface influence your etch rate and how your etching progresses. This is good and bad. Good is if you can introduce them intentionally, because this will allow you a deterministic etching. The bad thing is if you have inhomogeneities in your sample, that then controls also to some degree your etching. So in order to look at the kinetics, we used only islands which did not undergo coalescence, and we stopped recording the information for this graph the moment they coalesced, which is like at some point this small island coalesced with the big one, and at that point we stopped recording it, or we only started to record the larger island here. Island 4 is wonderful because it's particularly well behaved. It's the green one you can see here, and we can follow that one over a really long time. So you can see we recorded 10 islands in the end, which were very benign, well-behaved islands. But you also see, and let me point out that this recording is for 35,000 seconds. So each of these is many, many hours of image acquisition. And we generally did not correct for drift during that time, but drift was sufficiently low to allow us to do this. So the variation in growth rate is about a factor of 5. And I can tell you we don't really know why that growth rate for the vacancy islands varies so dramatically. It is not the bias voltage, not the feedback current, not the recording speed, and it might be the tip treatment, but we are not sure. We varied all these parameters systematically, and none of those correlate well with the observed changes in the kinetics of the growth. Does it matter? Yes, it does. If you really want to control right in a controlled way. So we do have some ideas about why the rate is different. It could be the local concentration of point defect, which etching is initiated. It could be that we have a much higher diffusion of the tantalum disulfide molecules on the surface, which changes it, which means the vicinity plays a role. Or it could be that we have a little bit of water in the system, and that concentration varies over time and influences the kinetics of the growth. Next step, we want to control the widening of the tip features. And let me give you another movie here just to enjoy. If you're at one of these step canyons here, things get really, really crazy. So you can see, you can follow the kinetics and all of that over a much longer time frame. And that's what we intend to do to solve the question about the mechanism and be able to replicate exactly how many, how large, in which direction do they point of these vacancy islands. And the next step is then, can we grow something into these vacancy islands and make lateral heterostructures? Let me go to the last one, and this is going to be a really quick one because I only have a few minutes left. And I mean, you might have noticed, and when I was giving my talk, I'm really curious about having data-driven studies, having sufficient statistical significance. And we're constantly struggling with the question of data scarcity in our work. And we're trying to find ways around that and kind of work in a more deterministic way at some point with STM. So I kind of convinced my colleague, Professor Balachandran, who is an expert in ML and AI nowadays, to think about how much can we really learn from data which are in the literature. Or finally, also from data, experimental data we produce, but the challenges are actually quite similar. So let me point out, we started this work and completed this work before the recent boom in AI, which is significant and overwhelming. However, a lot of what we learned here, I think, still applies. Because our main challenge was not the machine learning. Our main challenge was the question of data scarcity. And we looked at molybdenum disulfide, growth of molybdenum disulfide, because that has been studied most. And there's the richest, still not enough, but the richest repository of literature data available. Okay, so the first question is, what do we want? Our question was, okay, we just want to know what are the conditions of growth which are most likely to lead to a very nice monolayer of your MOS2, and which are the conditions which kind of do not lead to a monolayer, but kind of very rapidly give multi-layer samples. So I had a student who read was about 80 publications and extracted the information which is in the publications. And you can see that not all publications mention everything. And you never know temperature. How was it measured? People don't tell you. They just give you temperature. So if your growth is really sensitive to temperature, the metadata which are included in the publications are not sufficient to give you even an idea about what the error in the data could be. So we continued that. We sorted these publications out, and you can read our publication on that. It's very detailed on the machine learning as well as the curation of the data. And one thing you would think, which is really easy to get because everybody does it, Raman spectroscopy to confirm how many layers you have. So this is just one of the 9 synthesis variables we extracted. And the reason we use those, it's not a scientific one, is really because most people mention these 9. So even if you look at Raman spectroscopy, where your peak split correlates reasonably well with the number of layers, you still see a significant spread. You have those who claim single layer, but the Raman spectroscopy actually shows that the peak split is much larger. So we have those who claim multi-layer, but their peak split is much, much smaller. So that's when you get your outliers. So even something which is recorded by everybody, we went in and we looked at the spectra and compared them to the interpretation which is given in the publication. And even Raman peak split, you can have strain in the samples, which throws off your number of layers interpretation. So the same is valid if you look at images of your TMDs. Everybody has an image, but the question is sometimes it's a very large scale image, sometimes it's a very small scale image. So these are really difficult to compare because the top one gives you information about the homogeneity and where your data was measured, while the bottom one doesn't tell you anything about that. So having metadata with associated experimental outcome allows you to go back and quantify and benchmark your results. Shape is another one, which is rarely mentioned, but I'd like to point to John Redwing's work on MOCVD data, where that is really in a lot of wonderful detail done for a different growth method. So, how much did we learn? Did we learn anything new? I'm not sure. However, we could, with all the different machine learning methods, we could really faithfully reproduce and understand which one is the most important parameter. And I think that anybody who's grown stuff, that's probably pretty intuitive. You have the precursor temperature and you have the growth pressure, and then the time and the temperature of the precursor are the next two important ones. It is good to get that out of different machine learning methods. This is a so-called shadow descriptor, but we tried quite a few different ones. They all give the same information. This is information about essentially what the data we put in tell you. At some point, you want to kind of jump out from that data set and say, okay, let's say I want to grow a heterostructure and I want to grow molybdenum disulfide, but all the other conditions for the next layer or the previous layer have to be compatible with the good growth. So if I have a specific boundary conditions, what do I need to do to get a good growth? And that's jumping out of the current data set. So at some point you want to predict. So a random forest classification is one way which could get you there. It gives you a map which ties two things together. One thing is the outcome, which is color-coded here, a single layer or not a single layer, and it ties the two most important growth parameters to the outcome, like precursor temperature and growth pressure. So ideally, if you have enough data, you can construct these type of maps, which then allow you to grow a heterostructure. And for each material, you can or cannot find a spot on that map which gives you growth conditions under very different boundary conditions. What would you learn from this one? You really don't have a lot of data which allow you to go there. We are still very data sparse, and I think the LIST database at the 2DCC, the lifetime sample tracking, which has recorded, I think, sample information for a few years now, is really an important step into that space. But we also know that the quality of your metadata is incredibly important to this. Not just the number, the amount of metadata, but the quality. Are they benchmarked? How are the materials analyzed? Do you need more than you have right now? So I think this is still valid in the age of rapidly growing AI. Ideally, you also combine this with computational work, and I think that can help us to get out of this valley of data sparsity, so you can make more targeted and specifically positioned experimental work. So with that one, I would like to finish up my talk. I've shown you defects, studies of defects. I have shown you writing ginormously large defects with STM. And I've shown you where I really would love to go in the future, to have a more data-heavy program, which kind of combines all of these challenges which we still have in 2D materials. And, I sit at my computer all day, but my students are the ones who are in the lab and kind of come up with solutions to all these gnarly problems, program stuff overnight, and data, sleuth do the programming for interpreting and analyzing the data, and then, use them in all these fascinating and interesting ways. And thanks to all of them, thanks to the people who gave us money and samples. So it was a pleasure to kind of show you what we do with the material we get from your end for today. So thank you very much. And I'm happy to answer any questions. If you have anything you want to see, any other information, most of the work I've shown today is published, and I'm more than happy to talk to you about it.
All right, fantastic. So for people online, if you have questions, you can put them in the chat, or you can just unmute and ask them. Kelsey or Anthony, are there any questions in the room? Perfect.
Yeah, thank you, Petra, for the talk. I'm kind of interested in the tantalum sulfide. Where's all the material going? Like all of those atoms, where do they end up?
And that's a really good question. So we think some of them probably diffuse on the surface. We have seen some where you even detach a little slice and it's redeposited and reintegrated at another point of the vacancy island. But we do think that quite a few desorb, despite the fact that it's actually room temperature, but it's also vacuum, so that gives you a higher desorption rate than you would otherwise expect. They might be redeposited, at least some of them, on the tip, actually. But this is a big question which we would like to pursue. And I think that's a big question if you really want to go to deterministic writing of your vacancy islands and build your lateral structures. So we need to learn that. Absolutely.
Yeah, it's surprising that doesn't seem dependent on the tunnel current or the bias voltage.
Yeah. And I mean, not all we measured, we might try higher and lower, different combinations, but we did not see a change really in the rate by that. So that's why we think it's somewhat materials related in this case, and related to actually really point defects which are in the sample. And the way to try that out is you do a very sparse ion irradiation and you generate a few defects, and you see how that changes your response in the etching process.
And the surfaces, are they cleaved in vacuum, or are they?
It was. Let me think about that. This one was cleaved in a nitrogen backstream just before entering into the load lock.
Okay. Yeah. Thank you.
Anyone else? Go ahead.
Thank you for the nice presentation and interesting. I will have a few questions for both subjects. For the first one, the vacancies, which are the P-type vacancy, you said that you might have some vacancy below the transition metal into the layer. So you have a selenium vacancy, or you have it to the graphene layer, which is in the substance?
That's a good point. So this one is a few layer sample. So I think the graphene layer actually stops the diffusion of selenium if it is actually, becomes unbonded. And that's why we think we might have some clusters which form in the in-between layers. It's very clear that in this two-layer situation, we have a completely intact cover layer, but we do have something which is electronically changes the game beneath that particular defect. So geometrically, there is something below that defect. And our current interpretation that it is a selenium cluster. Would I put my hand into the fire for that? Probably. Yeah.
And the second
We have
question.
time for maybe one more quick question.
Okay, sorry. Could you manipulate the defects locally by the electric field into the STM junction or by charge injection or some other processes locally used by STM?
Can someone repeat me the question? I don't hear it really well.
Yeah. She's asking, can you manipulate the defects either by putting the tip over them and pulsing them, or are you able to do anything with them?
We probably could. So generally pulsing with this really high electric field, I think it's probably destructive. So if we do tip cleaning procedures, we generally rip a really large hole. But tip cleaning is not a controlled process. We have not tried to move them around, but that's a great idea. Yeah.
All right, and there was one quick online question. So Rafiq asked, any XPS done to confirm the presence of water on the surface of tantalum disulfide?
Not in this one. Yes. However, the experiment which is on our list is really to have very small water background pressures. We have now in our other chamber, we have a QMS, so we can monitor that and can do the counter experiment, which will give us that information. And then we can bleed in just a little bit of water. Water tends to be more aggressive in terms of etching. So we do expect a change there.
All right, well, we are right at 1 o'clock, so that is it for today. So let's thank Professor Reinke again.
Okay.
All right, thank you so much. And I will see all of you at the next webinar next month.
Thank you. And thank you for the opportunity. This was a lot of fun.
Yeah, thank you so much.
Yeah. Bye.